For me, it's a pleasure to introduce Angel Lozano. I think that Angel Lozano doesn't need an introduction at all. But and today he will talk about 5G. This is one of the hot topics we have now in the wireless communications arena. But before telling something about Angel Lozano, I would like to show one document that I found this morning when I was thinking a little bit about Angel. And I was surprised because I found this publication is from January 2000.
Yeah, I was there.
Do you remember?
I was there, yes.
You were there. I was trying to find you, but it was a little bit. It was the 100th anniversary of the Marconi's experiment in the US. Marconi was the pioneer trying to do some kind of wireless communication or wireless, sending some data. This was the place. And Angel, I was trying to look for you and even me, but it was not possible because the quality of the picture is not.
We need one of these image processing gurus to enhance the image.
Yeah, I was thinking the same. So we have some.
Pongoma or Marcelo, one of these guys.
They're trying to reconstruct. So this was the first time we met, I think.
Yeah,
we were just we
were younger, let's say.
Younger, a little bit. It's not a long time ago. So I wanted to share with you and with all the audience this picture that the day we first met, and some years after, a few years after, we met here at the UPF. So it was a pleasure to have Angel here joining the department 7 or 8 years ago. He has been really committed with the university, not only building the research group and doing brilliant research with us, but also with a high level of commitment with the UPF, being vice rector for research almost
6 years. Yeah.
6 years. So now he is in his sabbatical. So right, but he's here sharing with us the last research thoughts about 5G and see how this is going to evolve in the next year. So thank you for accepting the invitation. And
okay, thank you, Miguel. So these seminars are a good opportunity for us to showcase our research, and especially for those of us in minority topics, because even though this is a department on information and communication technologies, those of us doing communications are actually a small minority here. So this is a welcome opportunity. And just to show you graphically where my research is positioned within the IEEE, my field is communication theory, which is formal within the IEEE Communication Society, although having some intersection with the information theory and signal processing. Also, there is a very large committee on communication theory, IEEE committee, which I actually chaired for a few years. And my work revolves mostly around the activities, the publications, and the conferences organized by this committee. Okay, so with that prelude, let me get into the talk itself. And the subject are wireless networks. The talk has 6 sections, about 45 minutes. So my challenge, ironically, is to try to keep your attention away from your smartphones for about 40 minutes while I explain things about those very smartphones. And as a general comment, before I start, I'm not going to specifically talk about Wi-Fi. I'm going to focus on wide area networks that can be accessed anywhere. Wi-Fi is a great complement for hotspots, and we need it. But it's kind of unpredictable and spotty. And I'm sure you've all had your share of frustration with it. So let me go ahead and start with the first section, where I'll try to establish what those of us in communication theory, what we do for a living. So there are 2 metrics that drive our work, which are in fact intertwined. They are the user bitrate and the area capacity. And here I've placed them within a triangle that contains the 3 resources that we need to communicate data. So the first is bandwidth, which is to say spectrum. The second is energy, or what's the same, power. And the third is computational complexity. So let me spend just a few minutes detailing all these quantities and how they interplay. The user bitrate measures the number of bits per second that flow reliably to specific users, like yourselves. It's an important quantity, especially for certain applications, but not as important as the area capacity, which measures the aggregate bitrate over all users within a certain area, say a square kilometer, for instance. These 2 quantities measure your degree of satisfaction as consumers of data. The challenge we have here are the expectations, and this chart makes that point. Just ignore all the acronyms which correspond to specific standards. Just look at the two lines. So the blue line depicts the evolution over time of the user bit rates over wireline networks. So we've had ISDN, then ADSL, now fiber optics. And the yellow line depicts the evolution over time of the bit rates over wireless networks. And the issue is that wireless is always one order of magnitude behind. Okay? This is not surprising, given that a radio channel is much more challenging than a cable channel. But it does mean that your expectations are of a certain performance that you're used to, and you expect it over our networks as well. Okay, so this is what we're up against. This is a quote from a report by the company Ericsson, which I think describes very well these expectations. It says that wait times during web page and video loads causes mobile users' heart rates to increase 38%, which apparently is equivalent to the anxiety of watching a horror movie alone, which is a very remarkable baseline for stress. And then once the video begins, an additional pause increases frustration dramatically. Okay, so this is what we're up against as engineers. Now let's talk about the resources we need to quench this thirst for data that you have. The first thing that we need is radio spectrum. And even though there is an infinite amount of it, only a finite amount is actually usable. The portion roughly between 1 and 6 gigahertz, which we usually call the radio window. Below this window, the wavelength is too long, so the antennas are too big to be practical. And above it, the signals don't propagate very well. And they suffer a lot of attenuation. In fact, that's what the chart depicts. So this chart depicts the attenuation in dB per kilometer. So as you can see, it's almost zero over this radio window, and then it spikes up into tens or even hundreds of dB per kilometer once you exceed a few gigahertz. So because the amount of spectrum is limited, and we require more and more of it, it has become very expensive. It has become expensive to license it for exclusive use. So these days, it's roughly at €1 per megahertz per population unit. So a company like Vodafone or Telefonica, say they want to license 100 megahertz to use in Catalonia, which has 7 million people, they have to pony up 700 million euros just to have the bandwidth to transmit. Okay? It's a lot of money, but that gives them exclusive access to this bandwidth, and that avoids all the interference contamination that Wi-Fi suffers. Okay, so that's bandwidth. The second thing we need is energy to radiate, and well, what do I have to tell you that you don't know already? The most sought after things these days at airports and coffee shops are power plugs. And charging stations are now becoming pretty common, especially in the US. For now, they're free of charge, but I suspect that will change. In Amsterdam, they have at the airport these eco-friendly charging stations where you have to pedal to charge your phone. And in a sense, having to labor for power is already a form of payment, in a sense. So the critical point when it comes to batteries is to be able to spend the whole day without recharging your device. And we're close to that point already. So it's a resource we have to manage carefully if we don't want to have to force people to carry around chargers and spare batteries with them, which would be undesirable. Battery lives are one side of the energy equation, the more obvious one perhaps for us. But there's another side, which is that the biggest operating expense of companies like Telefonica or Vodafone these days is the electricity bill. Okay? And that gets passed on to us. Okay? So that's one of the reasons that things are so expensive here. So reducing power consumption is also very important for them, not to mention all the initiatives on green ICT to reduce power consumption worldwide. Okay, so we have spectrum, we have energy, and the third thing we need is computational complexity. And this one has various implications. The first one is energy again, not energy radiated, but energy spent processing signals. The second one is size. So a small wireless device is very different than a tablet, for instance, or a smartphone in terms of the real estate you have to install processors. And the third is cost, which is a very important variable in the marketplace. So these are the quantities we work with, bitrate and area capacity versus bandwidth, energy, and complexity. And we combine them into figures of merit. For instance, by combining the bit rate in bits per second with the bandwidth in hertz, you obtain something called spectrum efficiency in bits per second per hertz, which measures how well you're using your spectrum. Okay? Or if you combine the bit rate in bits per second with the power in watts, you get the energy efficiency in bits per second per watt or in bits per joule. So in our work, we mostly try to find new ways to push these ratios higher so we can maximize the bit rate and the capacity with certain resources, or we can minimize the resources to achieve a certain performance. All right, let me move on to the second section. I'm a history freak, and I could spend all the time I have and more talking about it, so I'll have to contain myself here. I do think that a bit of history helps understand why things are the way they are. So I'm going to spend about 5 minutes discussing some key steps in the evolution of wireless communications. And Mikel brought up Marconi, who's going to come up in the story. I did a small experiment at some point and asked a bunch of young people some questions about the origins of this technology that they are so addicted to. And the outcome was disappointing. Not surprising, perhaps, but disappointing. Younger generations seem to associate wireless communications with people and companies such as these and others like them. And these players have certainly played a part in the story, but they really are just the icing on the cake. These players have transformed the mobile phone into a dazzling computational platform that has exceeded anyone's expectations and that is an essential part of our lives. That's true. And yet, the concept of a smartphone is hardly new. As early as 1993, IBM launched a smart device called the Simon, which had the amazing amount of 1 megabyte of memory and a touch screen. And Nokia followed in 96 with their Nokia 9000, which was a similar device. Both were very big, like brick-size devices, very expensive and very heavy. And their performance was laughable by today's standards. They failed commercially, but not because the concept was wrong, just because it was ahead of its time. Now, 20 years later, of course, the time was right, and other players took the concept of a smartphone to fruition, as we're enjoying today. Anyway, this experiment with the youngsters made me think, and then there was an article recently on the IEEE Spectrum which pointed in this direction too. And so I got to thinking about which are the key breakthroughs that defined where we are and where, and I came up with the following 5 milestones. So in my view, the first breakthrough came in the 1860s when Maxwell unified electricity and magnetism in a wonderful set of equations. I spent some time at the University of Edinburgh, which is Maxwell's alma mater, and every morning I literally walked over the equations on the way to my office. These equations predicted the existence of electromagnetic waves, a prediction that was then verified by the German gentleman, Heinrich Hertz, a few years later, who then famously stated that he did not think that the wireless waves he had discovered would have any practical applications. He couldn't have been more wrong, and by the turn of the century, people had set out to use these waves to communicate information at a distance, initially Morse signals. Arguably, the first one to achieve it was Russian Alexander Popov, but the two people that history remembers are the eccentric genius Nikola Tesla and the more entrepreneurial Guillermo Marconi. Marconi was not just a resourceful engineer, but a great businessman, and he capitalized on his inventions to build an empire, the Marconi Corporation, which for years monopolized the ship-to-ship and the ship-to-shore communication. Okay? He was the only company doing that. This company and his technology jumped to fame when the Titanic sank in 1912. The Titanic's distress Morse signal was received by another ship, the Carpathia, which managed to rescue 700 people. These are recreations of the Titanic's Marconi room, very carefully done for the movie Titanic. So I'd say that like Maxwell and Hertz, these two guys, Tesla and Marconi, were really true giants in their time. So Morse signals gave way to amplitude modulation, and so human voice could be transmitted. And by the 1930s, we had frequency modulation. Here you can see one of the earliest car phone prototypes, big and bulky, but a real wonder back then. After World War II, 25 US cities deployed public telephony systems. Each consisted of a of a single transmitter blasting from a tower on the highest possible mountain. And only a handful of users could be served at a time. The typical wait to get online was half an hour. So in this context, in 1946, an engineer called Douglas Rink, working at Bell Labs, had a transformational idea, which he developed in a paper he called cell sites. So the idea was to divide any region of interest into small parcels, which he called cells, each featuring a separate transmitter receiver. So instead of a single transmitter blasting the entire region, you'd have smaller ones, each serving one of these cells. Okay? So in time, this would be called a cellular system. And Ring illustrated his idea with this picture, which it's kind of hard to see, but it depicts the coast of New Jersey and the city of New York. This is Manhattan over here. And these are the cells he proposed using circles. This divide and conquer idea was visionary, as we will see, but the technology to implement it simply did not exist in 1946. Okay, well, there are places and times that are special, and Bell Labs in the middle of the 20th century was such a place and such a time. So only 2 years after Ring planted the seed for cellular systems, and not far from his office, in fact, information theory was born. So that made it possible to quantify information with the bit as the universal currency, and to establish the maximum amount of information that could be transmitted reliably through a noisy channel. So in a very real sense, the information age began in 1948 with Shannon's work. The fifth and final breakthrough, in my opinion, came with the realization of a comment made by Richard Feynman. There is plenty of room at the bottom. The offspring of this comment was the integrated circuit with pioneering companies such as Fairchild Semiconductor, Intel, or TI that made it a reality in the 1960s. Gordon Moore, in particular, one of the founders of Intel, is credited with the observation that the transistor densities double roughly every 18 months. This Moore's law has driven the evolution of the integration of processors and memory to our days. So these 5 breakthroughs set the stage for the first generation of cellular systems, which were trialed by AT&T in 1978 in Chicago and Newark. Here you can see the paperwork from those trials. Each consisted of a bunch of cells, which are here shown as hexagons. The commercial deployment came in 1983, and this gentleman here is Martin Cooper, the guy who designed and made the first call from a handheld device. So following Ring's vision, these first generation systems were organized in cells, each featuring a central site called the base station, which is a transmitter receiver that connects by radio with the mobile devices. And then all these base stations are cabled into a network. So each mobile device, for instance, this guy here, connects by radio with the base station in its cell, and then the signals go by cable to the network. Okay? And then as people move around, their calls get handed off from one cell to the next. This first generation was followed by subsequent generations, 2G, 3G, now 4G. I guess those of us who are old enough have seen all these generations. Probably one every 10 years, just riding Moore's law to increase bit rates and capacity dramatically. Although I have to say, without any major conceptual breakthroughs. To dissect the progression of the area capacity over time, it's useful to express it as a product of 3 terms. So that would be the spectrum efficiency, that would be bits per second per hertz per cell, times the density of cells, so say cells per square kilometer, times the bandwidth in hertz. Okay, so that gives you bits per second per square kilometer. This guy we encountered a minute ago, Martin Cooper, the one who designed the first handheld phone, observed that the area capacity, this quantity, has roughly doubled every 30 months or so, which corresponds into a factor of about 1 million over time. Okay? So he actually went ahead and broke down this factor of 1 million, and it turns out that the lion's share, factor of 1600, has come from increasing the cell density, okay? With smaller factors that have come from having more bandwidth and more efficiency. These are just ballpark numbers, but they do make the point that when it comes to increasing the area capacity, nothing beats densifying the cell structure. And indeed, Ring surely would be amazed if he could see how far his idea has gone. So today, in the US alone, there are close to 400,000 cells. As you can see, they correlate with population density. And worldwide, there are about 6 million cells. Today, we're roughly 1 for every 1,000 people. Okay? So this is certainly a successful idea if there was ever one. So that's where we are today, with 4G deployed in most of the advanced world. In developing countries, they still have 2G and 3G. And just a couple of data points. There are 7,300 million subscribers worldwide, which is about 90% of the population. And just to put that in context, there's 2,000 million PCs in the world, personal computers. Okay? So the European Union exceeds 100% penetration, the US 110%, so there's more phones than people. And there are many nations, including big ones like India, that have more people with wireless access than with electricity at home, which makes you wonder how they charge their phones, but never mind. And final data point, a smartphone today has more computing power than the entire Apollo program that sent people to the moon. The expansion has been phenomenal, for instance, and very fast. For instance, in terms of internet access, wireless access has taken over from fixed access in just a few years. So in 10 years, we've gone from all the access was fixed to mostly 80% is mobile. So the future of the internet seems to be mobile. And using the area capacity breakdown I introduced, with a small twist, we can gauge the performance that today's networks can deliver. Okay? So let's see. The efficiency on a 4G network is about 1 bit per second per hertz per cell. Every cell serves about 1,000 people. And the total amount of licensed spectrum, including 2G, 3G, 4G, and all operators, is about 500 megahertz, give or take. So you multiply this, and you get about 500 kilobits per second for each of us. Okay? Now, most of the time, only a subset of us are active. So we actually get to enjoy a few megabits per second, which is a huge improvement over the 10 kilobits per second that was the peak rate 20 years ago. So we multiply that by about 1,000, okay, in 20 years, in 4 generations. I couldn't possibly detail all the advances that have taken us from 1G to 4G. Let me just briefly touch on one that has been my main research focus since I finished my PhD. It's called MIMO. It stands for multiple input, multiple output. And it consists of vectorizing the transmissions. So rather than transmitting a single signal from a single antenna, we transmit a vector of signals from various antennas. Say this vector X would be the vector of signals. And then if at the receiver we also have various antennas, what we observe can be construed as another vector, and let's call it Y. And these vectors are related to a matrix called H here. So the ijth entry of this matrix H would be the specific channel between the ith antenna here and the jth antenna here. Okay? So by inverting this matrix, we can recover at the receiver what was transmitted at the other side. Of course, it's not so easy because the observations are noisy. This vector n represents the noise here. So you can't just quite invert it. But with substantial signal processing, you can recover X from observing Y. Okay? That's what we do. This is MIMO in a nutshell, and it's already commercial. In fact, the smartphones you have in your pockets all have at least 2 internal antennas. And they are all receiving vector transmissions probably right now. So given where we are with megabits per second for each of us on a good day, plus Wi-Fi on the hotspots, do we need yet another generation? It's a good question, and apparently we do, because the hunger for bitrate is relentless. Right now it's growing at 57% a year, which means a factor of 10 every 5 years, a factor of 100 every 10 years, a factor of 1,000 every 15 years. Okay? So it's mind-boggling. Right now, 2017, we're at about 11 exabytes a month worldwide, going to 16 next year. Remember, an exabyte is 1 million terabytes. Okay? So it's just, like I said, mind-boggling amounts of data that are being sent. So we do need another G, apparently. And the research on 5G actually got momentum already 4, 5, even 6 years ago. And we've had a period of much excitement, what I usually call 5G mania, in my community. which is now coming to an end as the target deployment date of 2020 approaches. The idea is to have the first trials at the 2020 Olympics in Japan. So just so you see the scope of this 5G mania, these days you can get all sorts of 5G gear, t-shirts, coffee mugs, hats, whatever you want. Not many research topics, I think, have this luxury. This frenzy has also been feeding all sorts of initiatives, especially funding instruments that have popped up like mushrooms all over the world. In Europe, we have something called the 5G Public-Private Partnership, 5G PPP, which has been funneling millions of euros into 5G research for some time now. So in 2014, I co-wrote a paper on 5G with colleagues from Samsung, Huawei, Nokia, and other universities, which has had substantial impact. The paper outlined the direction that 5G has taken, which drive to the limit the three existing mechanisms that are indicated here. So MIMO becomes massive MIMO, densification becomes ultra densification, and the frontiers of usable spectrum get pushed aggressively. So let me briefly comment on these three research directions. So with massive MIMO, the idea is to go from today's tower top deployments or base stations, where we can house, say, a dozen antennas or so at most, so we can vectorize, but just in limited amounts, to having vast arrays deployed, let me see, here it is. Vast arrays of antennas deployed along the roofs and even the facades of buildings, or maybe on billboards, each one with tens or possibly even hundreds of antennas, okay? And camouflaged so they don't disturb the environment. Okay? This is the vision for the massive MIMO. The prototype's already out there. Here on top you can see a 64 antenna prototype built by Alcatel-Lucent, which is now Nokia. And below there's a 128 antenna design that came out of a European project. So massive MIMO is one direction to equip big cells with these huge arrays. And then ultra densification is a second direction, which would complement these big cells with lots and lots of very small cells. And terms such as picocell and now even femtocell have been coined to refer to these tiny cells, which in a sense will be competing with Wi-Fi. The third direction in 5G has been to push the frontiers of the usable spectrum. So remember that historically we haven't been able to use frequencies above 6 gigahertz because they don't propagate very well. Now with ultra densification, well, we don't need the signals to travel very far because the transmitters and the receivers are going to be close by. Okay? So we actually can survive with these attenuations. And there is reasonable hope that we may be able to tap frequencies up to 70, 80, or maybe even 90 gigahertz. Okay? The jury is still out on how effectively we can use these frequencies, but the expectations right now are very high. Okay, so we'll be broadening the amount of spectrum that we can use. Okay, that's in a nutshell what 5G is shaping up to be. Macro cells with massive MIMO, plus lots and lots of small cells using a wider range of spectrum. Now, looking beyond 5G, let me turn to my current research. Despite the great progress in performance, the structure of today's networks, and even the structure of the upcoming 5G networks, is really not very different from those we had 20 years ago. So the cell is still at the heart of everything. And there's an inherent problem with cells, which is interference. So when a base station sends a signal to a user, that signal does not only reach this user, as the nature of radio propagation, it reaches everybody. And for all the unintended users, this signal is interference that adds up to the noise. So keeping interference under control has been a favorite research topic for years, the problem that has kept lots and lots of people busy for a very long time. But when you think about it, what is really interference? Interference is actually a signal that's meant for someone in a cell, which is being received by someone else in another cell. Okay? So interference is determined by the cell structure, which is an artificial construct. So perhaps the time has come when we should move past the concept of a cell, which has, of course, served us very well, but which might have run its course by now. So we should perhaps start viewing the network as what it is, which is just a set of base stations serving a set of users. And rather than have each base station serve only the users in itself, we can have all the base stations jointly serving all the users. Okay? That can be done by applying the MIMO idea of vectorization across multiple base stations rather than individually at each one. And this is one of the premises of the ERC Advanced Grant that I'm running, the idea of having wireless networks without cells. Consider this two-cell toy example, where with a cellular structure, there is cross-interference between the two cells. So each base station does not care for the signal being sent by the user on the other cell. Okay? That's just noise for this base station. Now, if we remove the cells and we allow the two base stations to work together and jointly decode both signals, then both base stations care about both signals, and the interference now has become useful signal. So not only do these crosslinks stop being interference, now they have become usable. Okay? Now, this looks easy when you have only two base stations, but when you consider a network with hundreds or thousands of base stations, it's impossible to jointly vectorize all the transmissions. So one must carefully define local neighborhoods where each base station vectorizes its transmissions with a selected bunch of neighbors. Moreover, they should all be dynamic. So we should have a particular vectorization structure at a given point with base stations serving users in a certain way. And then as people move around or new users come into the system, we should have a different arrangement, different vectorizations, and so on and so forth. Okay? Without the rigidity of a predefined pattern of cells. This is certainly not easy, but now we have the computational power to face it, and we have lots and lots of data being constantly gathered and reported by your smartphones, which can help the network assess the best course of action at each instant. That's something that my student Rasul Nikbat is exploring under the umbrella of the Maria de Maeztu program in cooperation with Anders Johnson. So we're playing with machine learning, which is a new tool for us. And we can credit this work and this cooperation with Anders to Maria de Maeztu. This idea of getting rid of cells goes hand in hand with other currents of thought, chiefly the idea of deconstructing base stations. So just to take all the processors that reside physically at each base station right now and pull them together into a cloud. Okay? So if we could do that, we would get something called a cloud radio access network, which is now a very fashionable concept. So taking this idea to the limit, we could have the signal processing for the entire network on the cloud. And then the network structures, rather than being predetermined cells, will now become software-defined. Okay? The vectorizations could be software-defined. So instead of having these hardware boxes that are today's base stations, we'd have software running on a data center somewhere. Okay? This would offer incredible elasticity because no resources would be unused or wasted. And especially because the upgrades will come in the form of software updates rather than painful hardware replacements. So going from 5G to 6G, when the time comes, will be like going from Windows 7 to Windows 8, as opposed to what happens today, which is physical replacement of each of hundreds of thousands of base stations, okay? So, which is extremely expensive. So it's a very attractive idea, this cloud radio access, but it has some caveats. One is that the data centers cannot be in remote places, like, say, Amazon has them. They have to be nearby for the delays to be short. Okay? So we need one of these data centers every, I'd say at most 50 kilometers or so. And you'll see in a minute why delay is so important. But just to cover Catalonia would take at least a dozen or so of these small clouds, so local clouds, we could call them. Okay, so this is the final section of the talk where I'm going to outline things that I see in the horizon. Okay, so it's a little more ill-defined. If we view the evolution of wireless communications from the viewpoint of the human senses, we've gone from transmitting just audio in the early days to nowadays transmitting audio and video. Okay? And now we're starting to think about transmitting also smell and touch. Okay? If you're curious about smells, I refer you to the website of this company or notes, which is proposing devices to do just that. But here let me focus on touch, which has more implications and is now becoming possible thanks to haptic technology, which uses motion and pressure to recreate touch. Okay? This requires very short delays on the order of 1 millisecond or so, which is the time that it takes the brain to process physical contact. The end-to-end delay in wireless networks has come down substantially over time. It used to be as much as 100 milliseconds in 3G, even more. Today in 4G is 20, sometimes 15 milliseconds. That's the round-trip delay. And in 5G, the target is about 1 millisecond, okay? So that we can recreate touch at a distance. This is the reason that the data centers cannot be very far, and these 50 kilometers I brought up have to do with the speed of light, and that's pretty much it, right? 1 millisecond speed of light, 50 kilometers at most. Now, if we succeed with this 1 millisecond delay, which is far from easy, we'll open the door to so-called tactile wireless networks with lots of exciting applications, especially in remote medicine. So this could really be a game changer in healthcare. So you can, for instance, imagine someone who's had an accident in being taken to the hospital in an ambulance and having surgery in the ambulance, right, from a surgeon who is at the hospital. Okay? This could be possible, for instance. There's a lot of trials now on medical equipment being controlled remotely. And with 1 millisecond delays, you can actually recreate the touch at the other end. Okay? So you can actually operate at a distance. So that's very exciting. Another interesting issue in the horizon concerns the position of the smartphone as the dominant platform for wireless access. Nowadays, smartphones have become almost an extension of people's bodies, especially for youngsters. In extreme cases, literally an extension of their bodies. But this privileged position of the smartphone may be coming to an end. New platforms are about to proliferate, and we may soon be transitioning to an ecosystem of communication devices that, rather than portable, are wearable. I'm talking about smartwatches, smartbands, helmets, eyeglasses, even shoes and clothes, say jackets, such as this one, with lots of embedded antennas. My student Jordi George recently finished his thesis on the topic of wearable and wireless devices, and we just scratched the surface. There's lots of things to be done in this space. We could even see contact lenses equipped with wireless capabilities, although this is probably farther into the future. Keyboards and screens may become a thing of the past, progressively replaced by projections, so on-screen projections and off-wall projections. So this evolution is going to present major challenges for us because these new platforms are very small devices with tiny batteries. Okay? So we're going to have new constraints in terms of power consumption and complexity. The extreme of these will be in-body devices, say monitoring sensors, drug delivery systems, medical robots, or neural implants. The spectrum already reserved worldwide for these devices, but many things have to be rethought before they can be viable from a communications standpoint. At the other extreme, we have another emerging platform, the connected car, even the self-driving car, where we have big batteries and lots of processing power. So the constraints here are drastically different. So looking at the big picture, we're going to go from very homogeneous devices, the smartphones, to a variety of very heterogeneous devices. So we certainly have research challenges for years to come here in terms of communications. Okay, so my 40 minutes are up. So let me finish by acknowledging the support of various institutions, chiefly the European Research Council and ICRIA in the public arena, and then also Intel Corporation through their 5G University Research Program. And I also want to thank my students and postdocs, both the current ones, I mentioned a couple of them, in relation to projects, and those who've moved on to other places already. And I'll close the loop and leave you with a quote from Marconi. He made this prescient comment in 1932, shortly before he died. And I think that if he could see how far we've gone today, he would be proud. Thank you. Sure. Let me just backtrack. That's it? That's an easy one.
More comments?
Could you comment on if there are any health-related issues with all this wireless communication that is happening that is going to exceed as well in the near future?
Yeah, that's a very good question. Usually I query my students about it because they really don't have a sense of power. You know, they don't understand the difference between milliwatts and megawatts. One thing that has happened over time is that as the cells have become smaller and smaller, the powers have come down as well, right? So these older phones used to send a few watts of power. These days, our smartphones transmit about 100 milliwatts at most, usually less because they're power controlled by the base station. So these are very safe amounts of power. So in principle, there's no problem. And the tendency will continue to be to have less and less power because of the battery issues, etc. So if you put that in context, a home microwave is blasting 800 watts, right, when you're cooking something. So just the leakage to the door of the microwave oven is more than a few milliwatts. There's no problem with portable devices. Now, that said, I wouldn't have it next to my brain the whole day. It has to do as much with time as with power. So really it's the energy accumulated over time that matters. So sporadic exposure to high power is also not very harmful. Sustained exposure, accumulated exposure is what matters. Now, there's another issue, which is the base stations. And what happens here is that we all want to have great coverage, but we don't want the base station next to our home, right? Which is an oxymoron in a sense, or a contradiction. Because to have good service, you need the base station around you. Okay, that's what we face. So there's one of the main obstacles to densify networks today, actually, is zone permits. So it's very hard to get permits to install base stations because people don't want to have them. They want the service, they don't want the equipment. So this is actually the biggest obstacle to densification is getting the permits to install new base stations. It's understandable. Base stations transmit more power, a few tens of watts at most. It's still not a lot, but it's understandable that you don't want to be right next to it. But the power decay is very fast over distance. So as soon as you're a few meters away, it really is for sure not harmful. So I would say there's not much to worry about in summary.
Thanks a lot.
Thank you, great talk. I would like to know, in addition to the health issues, ethical issues related to this type of research. So mobility, where we are at each moment, what we do at each moment. So it's
yeah, it's a good question. This is something we have not had to worry about in the past, but now we may have to, because as we start using data gathered by the devices to make decisions, it may start to be an issue. So it has to do with anonymity, I guess. But this is something very new for us, certainly. I mean, you know, I'm used to filling out these, checking these boxes as a triviality. And now I have to double think about it. So it's going to be more of a concern. And the issues are the same ones, right? Anonymity and permission. So I think these days, when you update your iPhone, it asks you for permission to do analytics, right? To send data to Google. The same thing will have to come from Telefonica, for instance. Once they want to use your data to know where you are, they will have to get your permission to do it, yes. I have a hard time thinking about evil things that can be done with the data. But then again, once you begin, things can happen that one hasn't thought about, right? I can hardly imagine anything bad that Telefonica could do knowing where we are, but maybe I'm naive. Rafa.
Yeah, so it seems that here 5G is mostly focused on high bandwidth communication, but at the same time there's this big trend in IoT having low power networks like LoRa, Sigfox, etc. So is there going to be a convergence between the two? Because it seems that it's, even for conventional high bandwidth devices like phones, being able to have low power push notifications and stuff like that, as you would have typically in IoT applications, would actually be quite interesting. So, do you see this converging, or is this going to be is this going to remain as mostly different technologies for different applications?
Yeah, it's a good question. So in the past, we've had different networks to do these things. And I think that's the way to go. But unfortunately, I'm in the minority here. And the decision has been to integrate everything. So 5G will also support IoT. This is a big headache because these are very different types of systems, and now they have to coexist. In IoT, the problem is not the amount of data, it's the amount of devices. Right? The devices send very little data. They send reports and measurements and temperatures and alarms and things like that. So it's very few bits, but it's many devices. So they completely collapse the control channels, for instance. So it's a different problem, but they're forcing us to handle it using the same network. There are commercial interests here at play that go beyond engineering. I think from an engineering standpoint, I would keep them separate, but it has been decided to integrate them. So they want to be together. So 5G will support both IoT and smartphones and all these other gadgets. So it's a nightmare. Okay, let me be positive. It's going to ensure we have a job for many years to go. And papers to write and things to do. So let me take it on that positive spirit. IoT, the IoT guy, yeah, Rafa?
According to you, what is the biggest technical challenge to get there to these high efficiencies?
The biggest challenge, besides zone permits that I mentioned, is backhaul, which is getting the data, so cabling all these base stations, right? I don't know if you consider that technical or not. It has cost issues.
Yeah, but also, I mean, there's a lot of information that needs to go
yes.
backwards in these dedicated channels.
Yes, and it actually has good ramifications. So this idea of Cloud RAN, which is to have all the antennas hooked to a cloud, which is where the processing is done, right? So the antennas are dumb. They just have a converter and an amplifier, and they send the information, raw information to the cloud, and there you crank it up, right? As opposed to locally processing it as we do today. The problem now is the amount of data going over these cables that go back to the cloud, which is huge, right? So 100 megahertz times a few antennas, maybe 4 per site, right? Times number of bits to digitize the signals, you easily get gigabits per second of to flow, right? So you basically need fiber optics, which means you can only do that in places where you have lots of fiber optics. So Barcelona can support that. There's fiber optics to most apartments these days, but you go to Africa and there's nothing there, right? So what's going to happen probably is a big divergence between, say, Korea, China, Japan, and all these places where they have fiber everywhere, versus also parts of Europe, versus the rest of the world where they don't have the infrastructure to support it. And this diversion is accelerating. But that's a big technical challenge, right? And it's actually an information theory challenge. Compressed signals, there's a lot of redundancies in what you observe at different antennas. And people are working on that. So probably I put that on top of the list.
Thank you.
Oh, my own student, this is very dangerous.
Thank you very much for a nice talk. So I was wondering, in the last 20 years, we as a wireless engineering, or we are working on the how to model propagation, how to improve the bitrate all by analyzing the signal we receiving in all the environment. So when we come to the idea of this cloud RAN, so we have lots of data, we have, so also, you know, this machine learning coming to almost all the area. Do you think, is there any possibility so we lose our job in the future for this machine learning or all this technique? Because our job was to analyze these things, create algorithm, improve efficiency. So if machine learning can do better than us, why they need us? So
yeah, no, I'm not worried about losing my job to machine learning yet. But this is an interesting debate. It's almost philosophical, right? It's the expert skills versus okay, he's the right guy to answer that question, right? Machine learning people, but or many other people here better than me. But I would say that machine learning can do certain things very, very well, but nothing else. Like, you know, find patterns in data, identify faces of people. It's amazing, actually, yeah? But, you know, a robot cannot fold a towel, right, Hector? And probably won't for a while, thank goodness. So there's still, I think, a lot of room for experts like us doing work that cannot be complemented, right? So I think this is a tool we have to use, and you're trying to do that in your thesis, to do certain things. And there is going to be very powerful. But I think that there's still lots of things that we can do better in other ways, with other tools, like analysis or computer simulations, etc.
So I didn't fully understand the world without cells idea. So to me, what defines a cell is that this finite range of transmission. And what you were mentioning was a more like a moving cells with more efficient capabilities, but not. What do you mean by a world without cells?
Yeah. So in a cell, what happens is that as a user, your smartphone connects to the closest base station, right? That's actually what it does. It connects to the strongest base station, which is the closest one. And the rest of the signals that are received from other base stations are interference to you. So the point is to change all this and have all the base stations send signals that are meant for all the users at the same time, right? So you can vectorize. The problem is that it's a little hard to explain, right? You can vectorize the signals, as they do in a DSL, for instance, so that you receive only your share, right? And the rest of the interference avoids you, right? And I don't have a good picture for that, right? Except that baby example, right? But when you vectorize well, right, there are 10 base stations sending signals, and you observe a single signal and no interference, right? If you do it right, right? It's just mathematics, right? It's essentially matrix algebra. You can do that. You can vectorize properly so that you receive a clean signal with no interference, and vice versa. When you send your signal and everybody does at the same time, the base station jointly can decode all the signals and get all of them without interference. Right? That's the idea. You could do that with cells. Yes, you can imagine there are cells that cooperate somehow. Right? In fact, people have thought about this already. Right? Imagine that the cells are cooperating cells. Right? That's one way to see it. Another way to see it is forget the cells. Right? You have base stations because the cells really are artificial. They don't exist. There's no line on the ground saying, "Yep, end of the cell." No. It's based on powers. I hope that helps.
Okay. So related to previous questions about machine learning and so on,
Yeah.
no, but it's not machine learning. So the issue, so you're trying in some sense to maximize bit rate or efficiency or to define some function. Okay. So the very sort of model-based approach is let's try to set up the design space and let's try to optimize this and look for some optimization of the space of designs. Well, here it looks that so in some sense to bypass this by these regular cells or then move into something else. So this explicit optimization approach, has it been pursued or is it?
We do. The problem is that you could get into non-convex problems. In fact, even the two, I showed a baby example with 2 base stations and 2 users, that's a non-convex problem already.
That's the stuff of deep learning, so there's nothing convex in this world. Okay, it doesn't mean it doesn't work.
No, the optimization, you can formulate the optimizations, they're very complicated, right? Yeah, we optimize all the time. And sure, the problem is that so if I use machine learning, I don't know what the hell I'm doing, right? It's garbage in, garbage out.
No, I'm talking about optimization.
Yeah, sure. We're trying to do that now with Rasul. I think some problems can be helped that way, yes, but not all.
The last one, right?
Yeah. So when you said that there was this decision of IoT to move it together with 5G,
Yes.
I'm curious about the decision process. So where is this decided?
Yeah, there's a body that standardizes all these systems, right? So all these, 2G, 3G, 4G. There's a forum called 3GPP, which actually should be 5GPP now, but it's still called 3GPP, which hosts about 200 companies, including all the ones that you can imagine and more. And they get together, they have meetings once a month, and they standardize it. They produce all the standards, physically, the standards, right? So that's where they debate patterns and technologies, directions, and all that stuff, right? And that's what it was decided. And it makes for a very complicated system.
Okay. I think, is it short?
Before you mentioned the paradigm of cooperating base station. So what's the difference between multi-cell cooperation and cell-less system?
Well, that you're not hindered by what you had before, right? So you have sort of, the idea is to have a clean slate and start from scratch. Some attempts to have cells cooperating have not worked very well because you're still bound by the cell structure to some extent. So maybe you could do that, right? And eventually you get to the same answer, right? You should get to the same answer if you do it properly. But maybe just best to start from scratch and say, okay, now, in the old days, cell makes sense because they simplify the problem very much. But now we have so much computational power. Let's forget about it. Let's see what we can do. We have transmitters and receivers and nothing else. And so much capacity to process signals, and let's see what we can do. But like I said, if you do it right, you should get to the same answer both ways. Yes.
Okay. I have one last provocative question for Angelo. So you know that there are some Wi-Fi guys at the department, right?
Really?
So we don't use cells. So 3G tried to beat Wi-Fi, but it couldn't. 4G the same. Is going 5G to beat
Hopefully it's about time. This has been very frustrating, actually, because Wi-Fi is a very poor design.
But it's working.
It's working, yes.
Most of the people right now is using Wi-Fi.
There is this saying that says, "Good is the enemy. Better is the enemy of good," right? So it's a very poor design, very simple, and it works very well over short distances. Every attempt to overrule it in hotspots has failed, right? And 5G will be another attempt, which may fail again. What should happen, I think, is an integration, right? So 5G should stop worrying about hotspots, cover everything else, cover IoT well, cover short delays, cover the outdoors, and then integrate with Wi-Fi so sort of declare defeat for hotspots and make a pact with Wi-Fi and join forces. That's what I propose.
It sounds good. Okay. Thank you, Angelo.
Okay, thank everybody.